All right, welcome back, students. And this is Solutions Part 2, I guess you could call it. And as we talk about Part 2, again, a reminder that a solution is made up of two key parts, and that is the solute and solvent. That's going to be key for you guys to know, so make sure that you remember what those terms are. And that's going to come into play today as we go through. We're going to quickly review something from yesterday, and that is factors that can affect solutions. And then we'll talk about some other factors as well that we didn't talk about. Factors that affect the rate we mentioned briefly. And we said the rate is how fast it dissolves. And a lot of these you could probably figure out yourself. We said the first one is not something that we can actually affect, and that's an inherent solubility, and that's its natural inborn ability to dissolve. There's certain things inherently, you have certain character traits that are inherent to you as a person, and that comes from your DNA code, from your parents. That's not something that you can change or whatever. Same thing here. Depending on the compound, some things naturally dissolve better than others. That's just the way it is. The next one is the one that we can affect, and that is the frequency of collisions between solvent and solute particles. In order for something to dissolve, yesterday we watched that little video that showed solvent and solute particles coming into contact with each other in order to dissolve. And the more often they come into contact with each other, the more likely that that's going to happen. Or if I slow down those collisions, then that slows down the dissolving process. Usually, though, we want to speed up the dissolving process, and there's several things that can affect that. One we said was stirring, and that adds kinetic energy, which speeds up the molecules. So, the kinetic energy of my arm, moving the spoon, moving the water, all of that transfer of energy all the way down to the molecules of whatever it is I'm trying to dissolve. So if I'm putting some Country Time lemonade into some water, put the powder in, stir it. The reason I stir it is to dissolve it faster. It would eventually dissolve on its own, but if I want it, within a minute or two, then I stir it. Temperature is another one. If I change the temperature up or down, if I change it up, I'm increasing the temperature, which means more collisions, and it's able to dissolve faster or quicker. And then the last one we looked at yesterday was surface area. And surface area was this idea that the more you have exposed, the more collisions you're going to have between solvent and solute particles. We use the example of like granulated sugar, which is just like a spoonful of sugar. You put it in, and we're not going to break out into singing here from, Mary Poppins. But if you had a spoonful of sugar and you put it in a glass jar and you had this exact same amount of sugar, but it was in a sugar cube, the spoonful of sugar would dissolve faster because there's more of it exposed to the solvent, the water. So there's more collisions. In the sugar cube, only that which is out on the outside. Everything else, all the other sugar that's on the inside is making zero contact, or there's zero collisions between the solvent and solute particles until the outside dissolves away. And so it takes a lot longer to do that. So that would be the factors that can affect the rate at which something can dissolve, and you would want to know that. Those would be important for you to know. Now there are some other factors, and they don't necessarily have to do with the rate, but rather with the solubility. And if you remember, we talked about something that's soluble, or if we say we're talking about solubility, we're talking about something's ability to be dissolved. So this is not the rate, even though some of these can affect the rate. This has to do with its ability to be dissolved. So that's what we're kind of talking about here. And the first one is temperature. And this is going to work a little bit different for solids and liquids versus gases. For example, solids and liquids, if you increase the temperature, then generally speaking, they become more soluble. With a gas, typically they become less soluble. And probably a good example of this would be, in terms of a gas, if you think of soda, the warmer a soda is, the sooner it goes flat, okay, because you're adding energy. So what does that do? The gas molecules, the CO2 molecules move faster, and they try to seek The faster they move, they go to the top of the glass and they seek to escape. They have more energy to do that and to roam, and they escape into the air as a result of that. So that would be the difference there. Whereas solids and liquids, you increase the temperature, and generally speaking, they become more soluble, or you can dissolve even more of a substance in there. So that's kind of key to remember. That is a major difference between those two. Solids and liquids, as the temperature goes up, solubility goes up. With a gas, temperature goes up, solubility goes down. That would be something that you would want to write down and make sure that you know. And here it is. I'll put it up here. As temperature increases, solubility increases. We call that a direct relationship. So as one goes up, the other goes up. With gases, this would be an inverse relationship. As one goes up, as the temperature goes up, solubility decreases, which is why typically with a soda, once you open it, you stick it in cooler. Why? You lower the temperature. It helps keep that gas in there. The cooler you get it, the longer the gas is going to remain in the substance. Okay, the second factor that can affect the solubility, and this generally only applies to gases, it doesn't really affect solids and liquids to any great degree, is pressure. And basically, generally, the way this works, the more pressure you have on something, so if I increase the pressure, then the solubility goes up. So as the pressure increases, so does the solubility, or its ability to be dissolved. And again, a good example of this is soda. When you get a can or a 2-liter bottle, it's under pressure. Why? To keep the gas in there. When I release that pressure, open the can or open the bottle, what do you see happen? A bunch of bubbles rise to the surface. That's the CO2 gas trying to escape, and some of it does escape. Not all of it, but some of it does escape. Now, if I put the lid back on, I can reestablish the equilibrium there, and the can or the 2-liter bottle will establish pressure again and keep some of the gas back in there, but not quite as much as was before, because some did escape. And so again, as pressure goes up, solubility goes up, and that's part of what allows gas to be dissolved in something like soda in the first place. So that would be some factors that affect solubility, and again, those would be important to know in this chapter. And so here we go. As pressure increases, solubility increases. Okay, what we're going to deal with now is something we're going to spend a fair amount next several days in class. This is one of the things that we're going to really, really concentrate on. No pun intended there. Actually, yes, it was intended. And we're going to talk about measures of concentration. And measures of concentration, when we talk about something being concentrated, we're comparing how the solute particles to either a volume or a mass of the solvent or solution. In other words, how much solute is there compared to solvent or solution? Sorry about that. And there's kind of two phrases. We could say that a solution is concentrated. We sometimes think it's a strong solution or concentrated solution, and that has a large amount of solute. Or we can say that it's diluted or a dilute, okay, which means it's a solution containing only a small amount of solute. So it's not very concentrated. It's not very strong. An example of this, let's say you buy some orange juice concentrate, so the orange juice that comes in those little cans, and you have to add like 3 cans of water, to get normal orange juice. Well, you could add only, let's say, 1 can of water. Well, then it would be really, really concentrated. Probably wouldn't taste real good. Or you could add, let's say, 5 cans of water and it'd be really diluted and still wouldn't taste really good. Okay, so that would be what we're talking about in terms of concentration here. And there's several ways to figure this out. And all of these involve math, but they're fairly simple to set up. Matter of fact, the first one here is something that you kind of already know, and that is percent by mass. It's very, very similar to percent composition that we did earlier this year. And this is the formula here, percent by mass. And basically, to break this down, if you remember, anytime we do percent of anything is part divided by the whole. And in this case, the part is the solute divided by the mass of the solution. And then that answer times 100, or you can kind of cross out the times 100 there, because you're going to get a decimal and you just want to move the decimal over 2 spaces to the right. So that's why the times 100 is there. And that times 100, just so we can kind of understand it, this times 100 right here would actually be over to this side. It's not actually underneath. It would be after the division is done, then you would multiply by 100. So just so we're aware of that. All right, let's take a look at a problem here. So let's start with, here's our problem. Find the percent by mass of 15 grams of magnesium bromide is dissolved to create 175 grams of solution. And we're going to start with our basic formula, or generic, is percentage equals part divided by the whole. What's the part? It's the solute, and the whole is the solution. So I'm going to set up my percentage is going to be equal to, what's the solute? It's 15 grams. How do I know the 15 grams of magnesium bromide is my solute? How do I know that? Well, it tells me I have 15 grams of magnesium bromide. It's dissolved. Well, what's the one that's always being dissolved? It's the solute. Okay, the solution is the whole thing altogether. As a matter of fact, it tells me here that 175 grams is my solution. So if I was to set up the equation, it would look like this. 15 divided by 175, and again, this should be right there in your notes, so if you're kind of setting up the problem yourself. And then your answer would be 8.57% if you completed the problem. And so that would be how you do that percentage. And again, another way to do this would be if I had, let's say I didn't know this. So let's say this was my X here. So I was actually looking for this, and I did know my percentage. Let's say my percentage was, 10% in the problem. I could set the problem up a little bit differently and solve for X. So that's another way I could do it. Now, granted, that's not actually the problem in this case. Let's go ahead and do another one real quickly. And we have find the percent by mass of 20 grams of solute is dissolved in 100 grams of water. And again, we want to go part divided by whole. In this case, we have a little bit different situation. And we have our 20 grams of solute. It tells us it's the solute, so we can put that up right away. But you notice it tells us we have 100 grams of water. Well, what's water? Water is my solvent. Well, what goes on bottom? It's solution. So I'm not told what my mass of solution is. I'm only told what my mass of my mass of solvent is. So I know solvent and I know my solute, but I don't know my mass of solution. Well, that's not a problem, because can you figure out your mass of solution? Yeah, because what makes up a solution? Solvent plus solute. So if I put these two together, okay, the 100 plus 20, then that would give me my mass of solution. And so sometimes you have to read the problem closely to make sure, what is it actually giving me? Does it actually give me solute? Does it actually give me solution? Or did they not give me solution and they gave me solvent instead? And then I'm going to have to add my solute and solvent together. So sometimes that you'll have a problem or a question like that, and what they're wanting to see is, do you understand that solvent and solute go together to equal solution? And so you have to just pay attention to what is being given you. Don't assume that the numbers or values they give you are exactly what you're going to plug into the equation. And so you want to pay attention to that. So that would be the first measure of concentration, percent by mass. It's probably the easiest one. Not that any of them are incredibly hard or difficult. I think also on your notes you have percent by volume, and it works almost exactly the same way, except instead of mass, which would be grams, you would be using volume, which would be liters or milliliters. So you would do it the exact same way. So I'd like you to do the last problem in your notes there that you already have given to you, and attempt to solve that on your own. All right.